so much, Luis. Really interesting research, and we appreciate you sharing it with us. All right. The next person on my screen, I believe, Michael, you're up next. Would you like to share your screen?
Sure.
And while you're doing that, I can introduce you. So, Michael Zeinhofer he received his doctoral degree in astronomy and planetary science from Northern Arizona University. He has a master's in applied physics with a concentration in applied science as well, and research experience in cratering of planetary surfaces and exoplanetology. He was an adjunct instructor in astronomy at Western Connecticut State University, um, and I conducted research there on the telescope equipment as well as public observing nights. He has been with us at APUS, I think, for almost a year now. Is that right?
Uh,
You can correct me if
Almost
I'm wrong on
four
that,
years.
but oh, okay. Oh, awesome. Well, we are so sorry. I lose track of
It's
time. I
okay.
don't even know how long I've been here, but we are lucky to have you here and
Well,
very interested to hear about the presentation. So I'll turn the time over to you. Thanks.
all right. Well, thank you. So yeah, I appreciate Dr. Miller the introduction, and I'm going to give just a brief presentation essentially on my poster, since the poster has pretty much the same information as my slides, but uh, I've been working on a project on asteroid 4 Vesta and looking at the impact craters, and I just wanted to provide some preliminary investigations of what was found so far. So just as a brief introduction, Vesta is the second most massive object in the asteroid belt and was the first asteroid to be visited by the Dawn spacecraft in 2011. Dawn actually went into orbit around Vesta around July 16th, 2011, and then exited its orbit to move on to Dwarf Planet Ceres around September 5th, 2012. Now, the Dawn space mission did find that Vesta's surface is dominated by impact craters of all sizes, which is not surprising since it's in the asteroid belt. You'd expect there to be quite a significant amount of impact cratering across the surface. We see this with a lot of planetary bodies like the moon. The impact craters on the surface are central to understanding the geologic diversity of the body. However, there have been several studies already conducted on the impact craters on Vesta. So usually the question that's asked is, if there have already been previous studies on these impact craters, why would you continue to look at the impact craters on Vesta? Well, to answer that question, these were smaller studies. And usually when we look at impact craters, a lot of studies will look at particular subsets like just fresh impact craters or craters of a certain diameter size. And that's what we see here. The other data sets were of craters around 0.7 kilometers or larger in diameter. And there was only about 11,000 craters that were counted in the study by Liu et al. 2018. And with that being said, it was just looking at the latitude, longitude, and crater diameter, as well as some of the depth measurements, which can tell us a lot about the body, but there's more that can be uncovered. Other preliminary studies looked at craters greater than or equal to like 4 kilometers in diameter, with 1,800 craters being observed by Marachi et al. 2012, and then Vincent et al. 2014 also looked at only readable craters, looked at their crater depth and their diameter, and found that there was about 1,025 craters in their catalog. So providing more evidence on these impact craters really does help. So this prompted me to go ahead and look at a preliminary investigation of impact craters greater than or equal to 0.5 kilometers in diameter, not only looking at the crater depth and diameter, but also looking at the morphological properties, so what their interiors are made of, as well as their morphometric properties, what their shape is, to help understand Vesta's surface and subsurface properties. So craters were identified using the Java Mission Planning and Analysis for Remote Sensing, or we just call it JMARS. It's so much easier to say. Crater application. The craters were counted using the 3-point crater counting routine found within JMARS. You click 3 points around the crater rim. It infills a circle, gives you the crater diameter, and also gives you the longitude and latitude of the impact crater. Visual investigations were done using JMARS, both using the high altitude mapping orbit, or the HAMO global mosaic of Vesta, has a resolution around 60 meters per pixel. This is from the Dawn spacecraft. What I was looking for was the ejecta blankets materials thrown out after impact that surrounds the crater. This can tell us a little bit about movement of material across the surface. These ejectomorphologies are really important, and I'll talk about them a little bit later in this presentation. I also looked at crater preservation, which I created a crater classification scale for Vesta ranging from 0 to 5, 0 being a ghost crater, which is really not that visible, to 5 being a fresh impact crater. This is similar to the preservation scale that we found on Ceres, as well as a similar scale of 0 to 7, which is known to be on Mars. And then I also did a crater depth and rim height calculation by taking the average of 3 profiles using 2 different methods, using the mean sphere profile, which is saying that Vesta is a perfect sphere, and then the oblate sphere profile, which says that Vesta is an oblate spheroid, which is more in line to what it actually is. The reason why you do this is the mean sphere gives you these kind of averages across the surface, while the oblate spheroid will help keep the local topography differences across the body. So it's good to have values for both the crater depth and rim height in both of these models. So the preliminary results actually show that there was about 115 impact craters between 88.15 degrees south and 80 degrees south. I haven't gone further than the South Pole for this particular study. I'm working my way up. Crater diameters range from about 0.51 to 5.74 kilometers, with crater preservations ranging from 1 to 5. There were no ghost craters found, which is consistent with findings on other bodies. 26 craters displayed a continuous ejecta blanket, which is similar to what we see on the moon, meaning it's a drier body. While the ejecta-mobility ratio, the EM ratio, which is the radius of the crater divided by the radius of the, the radius of the ejecta divided by the radius of the crater, was calculated for the 26 craters. And the average EM ratio is about 2.5, which I'll talk about that in the next slide. Crater depth versus diameter was also investigated. And as you can see here, the number of craters, there's significantly more smaller craters than we do see with larger craters across the surface in this select region of the South Pole. And that's not too surprising, because we normally just see more smaller impacts across the surface of bodies and it increases the sample size. So ejecta mobility on Vesta, as you can see, we have crater diameter at the top image. And EM ratio, you can see that most of them fall within this 2.5-ish range, and with some being a little bit higher. And then the depth diameter relationship all fall within a particular range. And the average depth diameter ratio, I'll talk about in the next slide. But just to note that these error bars are standard error bars for both values seen. Now, what's really interesting is that the EM ratio is actually higher than what was calculated for Ceres, being also an asteroid that was investigated by Dawn, at 1.5. So Ceres has an average value of about 1.5, and with Vesta, it's about 2.5. So you might say, okay, that's an interesting value to see for a body that is also found within the asteroid belt. And then further investigation notes that it's actually much lower than the average value of 10 for the lunar highlands. So this in itself made me look at
you've got about a minute left.
Okay. This made me look at some of the other values, and across the solar system, Boyce et al. 2010 provided a value of layered ejecta, which is more wet ejecta, about 2.35. While Mars, we see a value about 1.5, and Ganymede between 0.7 and 1.1. So the values for Vesta are slightly higher, but fall within the range of what we see with the layered ejectas and some of the average layered ejectas across the solar system, even though it's continuous ejecta blankets. So it could be that Vesta's low surface gravity may be influencing the factors that we're seeing, as well as the smaller sample size. So further investigation will need to be done. While the crater depth diameter ratio is actually what we'd expect for the simple craters, the small craters, to be around 0.2. So in all, I'm going to continue data collection for the impact craters to continue looking at their morphologies and morphometric properties to compare with Ceres and other planetary bodies to really understand the surface properties of Vesta. Thank you.
Thank you so much. And I'm so sorry to make you rush at the end. This is
no, it's all right.
work, and really appreciate it. But yeah, this was really, really interesting. Thank you so much for sharing this with us today. I think we're gonna have people just keep putting questions in the chat and in the Q&A, and and we'll take them all at the end just to make sure that we get through everyone. And let's see, the next person on my screen is Jason. Jason, are you good to go next? Do you want to start working on sharing your screen and I can introduce you while you do that?
Sure.
Jason, awesome. Jason Casey is a software engineer with over 20 years of experience, currently working at Lockheed Martin. His lifelong fascination with astronomy has guided his path, leading him to pursue a master's degree in Earth and planetary sciences. Combining his extensive IT experience with his profound interest in the cosmos is a major career goal. Jason hopes to one day share his wealth of knowledge by teaching astronomy at both high school and college levels. Together with his family, Jason cherishes traveling across the country to witness celestial events like the recent total solar eclipse and the aurora borealis. So Jason, we're excited to hear from you today, and I'll let you take it away.
Thank you, Dr. Miller, for the introduction. I really appreciate it. So yeah, my name is Jason Casey. I'm a graduate student at American Public University, and my poster presentation today is on the role that sublimation plays in Pluto's atmosphere. There's kind of like a chicken and egg experience with Pluto's atmosphere, in that with sublimation, there are all these factors that play into cause sublimation to happen. So you can't just talk about sublimation on its own. You have to talk about all the things that play a factor here. So with sublimation, it's an endothermic process. So the surface actually ends up getting cooler as the sublimation happens of the nitrogen ice and that's on the surface. There's also methane ice as well as carbon dioxide on the surface, which is also the same constituents that make up the atmosphere. So as the sublimation occurs, the surface gets cooler, and as that sublimated gas rises and it's warmer, we actually get a very strange atmospheric profile for Pluto, which is unique in our solar system. We actually have a Earth-like stratosphere where the temperature increases in altitude at the beginning from the surface, and then it behaves like, it'll behave like Earth's mesosphere, and then eventually up to the exosphere. But what ends up happening here is that you have the temperatures rising to as much as 110 degrees Kelvin at around 30 kilometers, and there's this vapor pressure equilibrium with the surface. So that's the big thing here, is that the temperatures are so cold on Pluto, and volatiles such as nitrogen and methane and carbon monoxide, they have such such volatility that they easily turn into gases. So this situation is similar to like sweating on the skin, where your skin cools when you sweat. So you can see in the lower picture the temperature profile of what was observed with the New Horizons spacecraft that entered the Pluto system in 2015. You could see that the black line cuts all the way across to 100 degrees Kelvin and then starts to cool off again once it gets up to that haze layer. Now, the sublimation's main location is in the region called Sputnik Planitia, which is the left section, the western section of what people call Pluto's heart. And it's this giant depression from an impact crater that can be, is over 3 kilometers deep and is the largest cold trap and source of the nitrogen ice deposit on the dwarf planet. So its location, it actually stretches across multiple zones, the diurnal zones and tropical zones and Arctic zones and things like that. So when the different insolation from the sun happens, it will change the amount of sublimation that occurs. And it actually transports from the northern area, Sputnik Planitia, down into Tombo Regio and other areas with the katabatic winds that come down and scoop it up, which then further turn into bring the winds up and creating the atmospheric circulation that occurs on Pluto and helps transport the nitrogen and the methane and carbon monoxide up into the atmosphere. So all of that comes up and it moves in this cycle through the Pluto atmosphere, and eventually what happens in the middle, as the molecules move up, it starts to form these haze layers, and Pluto has over 20 haze layers that are made up of all of the sublimated volatiles that came up from the surface. With solar radiation that comes in, there's photodissociation and photoionization that occurs, and it ends up breaking up the nitrogen and the methane and forming hydrocarbons and nitriles that some of them end up sticking to each other and causing different light scattering and things like that, which end up giving Pluto that blue haze, color that you see, very similar to Earth's atmospheric blue. Some of these molecules, as they get heavier and stick together, they start to condense and sink to the surface, and they form these layers over Pluto where it's darker with a lower albedo. One of the interesting things about Pluto is that it has such a varying albedo that you have different insolation levels causing different sublimation processes across the dwarf planet. And all of this is caused by how crazy Pluto's orbit is around the sun. Pluto's tilted at 17 degrees to the ecliptic. It's also almost turned completely on its side at about 120 degrees. And it takes 248 years along its extremely eccentric orbit to go around the sun. So this leads to very extreme seasons. It has seasons like Earth, but not like the way we experience it. And these levels, these seasons are so varying that there are decade-long or century-long timeframes where parts of Pluto are in permanent darkness or in permanent sun. So as Pluto moves through its orbit, it changes how much sublimation occurs based on the amount of thermal inertia and insolation that happens from the sun. Right now, Pluto is past its perihelion, on its way to aphelion, and what's going to end up happening is that the atmosphere is going to start to collapse and possibly completely collapse. But yeah, there's so much more that we could talk about this, but I know I'm over time. So thank you very much. I really appreciate this opportunity to present this research.
Thank you so much, Jason. That was fascinating. Pluto is really an interesting object and very timely with all of the attention that dwarf planets are getting lately, and exoplanets as we, discover new worlds. Understanding those in our own solar system becomes so much more important. So, thank you so much. It was a fantastic presentation. Really appreciate it. Let's see. Ian, I was going to have you go next, if that's okay. Are you there, Ian?
I am. I'm sorry. Sure, that's fine.
No problem. All right, I will share your slide for you. And while I do that, Ian Dove is one of is a student here at the American Public University System. He is also a software engineer, his day job, and he is part of our exoplanet research group here at the university. He's actually the lead for Team 1, which was our pilot group. They've done a fantastic job, and I think the research that you're talking about today comes from that program. So, Ian, I'll let you take it away.
Thank you. Good afternoon, everybody. My name is Ian, and I wanted to talk to you all about the trials of doing exoplanet research in a virtual environment. So we meet and do everything virtually. There is no in-person, and it's been an experience. So to start off, the APUS Exoplanet Research Program was started in 2023 to allow students and alumni to observe, collect, analyze exoplanet data with the guidance and oversight of professors and the eventual goal of publishing a paper. The team members were chosen through an application process, and those who were accepted became the founding members of Team 1. Each member brought skills from outside the program that helped to provide a solid foundation for building a strong and cooperative research effort. To elaborate, I brought some of my software engineering skills. My counterpart, Bridget, is a published author, and she has been invaluable when it comes to working on papers, research. She is unfortunately couldn't be here with us today, but she was a big chunk of this project. By leveraging these skills, the team is able to achieve actions quickly and efficiently. We plan, schedule observations, and analyze data. Team members and professors interact via virtual methods through the messaging apps Slack, and we do video conferences through Zoom. Work and data we typically share through a file sharing app, and during the meetings, the teams, we routinely discuss planning observations via a schedule that we created to kind of give us an idea of what are the best planets to observe during the current monthly conditions. The only one we have kind of trouble getting around is weather. sorry. The APUS is a telescope located in West Virginia is the primary telescope we use for observations, but we do occasionally have access to observatories in Utah and the potential for observatory use in California, though we haven't been successful getting one working there yet. So Team 1 usually meets weekly to discuss current progress, plan future, and analyze data when it's available. During these meetings, the team works on a paper with the intent of publishing. A typical meeting involves discussing ideal planet candidates and planning for observations using the transit method. Team 1's selection process is based off that shared calendar to collect the best candidates based on a team set criteria for optimal observation conditions. The teams meet with the professors every other week to cover topics and results of the team meeting and ask for guidance and advice on current works. Through trial and error, the team has learned which methods are ideal and can streamline future planning. The team researches and tests new software to help with data analysis and reviews current progress to identify and address weak areas. So some of the software we're using right now is, for instance, NASA's Exotic. And we are using this to kind of take exoplanet data and output light curves. As the team learns from their mistakes and grows, they will continue to evaluate and adjust to optimize time and performance. Working in an entirely virtual environment has proven to be sustainable and achieved results. Despite some setbacks, overall progress is moving forward. So one of the interesting things I love is every setback has not discouraged me. We've had instances where data has been a little funny due to an alignment issue with the telescope, but I personally found that fascinating and didn't consider it a failure because while we did not get the desirable data, we did get something and it was a learning experience. Currently, the APUS Exoplanet program is in the early stages of forming a second team. Using lessons learned during the formation and implementation of Team 1, Team 2 can now start up and begin their work more quickly. In addition to the new team, we are also looking to expand access to more telescopes to include sites in the Southern Hemisphere. The ability to meet virtually and share information and team member skills has allowed the exoplanet research team to succeed. It has allowed students in alumni to conduct publishable research and gain experience and skills working in a research environment. While the program is still in the early stages and we are expecting to run into more setbacks and delays, we will continue to assess and adapt to issues that strengthens the program for future generations of virtual researchers. Bridget and I feel strongly that this opportunity has been an excellent experience to explore exoplanet research and work as a team to achieve scientific results. The ability to operate in this virtual environment has opened new possibilities that we could not otherwise have participated in while attending an online-only university. We are very proud to contribute to excellent program and look forward to paving the way for future students and researchers. And that concludes my.
Wonderful.
So,
Ian, thank you so much. This is a fantastic presentation. And let me say that, at APUS, we are so proud of you and Bridget for all the work that you've done on this and paving the way for the next teams and make it. You've done a fantastic job, and this was a great presentation. Thank you very much.
thank you.
All right. Let's see. Our next presenter will be Dr. Sherry Curtis, and Sherry, I'll let you go ahead and start pulling up your slides while I introduce you. Sherry Curtis Rogers is a professor of physical sciences and a STEM academic specialist at Dodge City Community College in Dodge City, Kansas. In the fall of 2022, she was selected for the NASA Astronomy Activation Ambassadors Program and spent time at the NASA IRTF on Mauna Kea. So, man, that's an amazing experience. Congratulations to you, Sherry. Very cool. And we'll let you go ahead with your presentation. Thank you.
All righty. Yes, it was very cool. I highly recommend. Highly recommend that. This summer I took a class and I was our final project was being tasked with basically selling a trip to Mars to investors. And that one, depending on the administration, is still sometimes the goal. So what I have here, each one probably warrants their own individual poster, but it addresses some of the health risks and possible technologies for countermeasures, and then just to get to Mars, and then some of the technologies we could use to stay on the surface of Mars for a length of time. So on the left corner up there, we'll start with radiation because that is my favorite. And we've known for a long time the risks of radiation once we leave the Earth's protective atmosphere and magnetic field. And we are fortunate to have a fair amount of data thanks to the ISS for various exposure rates. And it's a little small, but you can see that on the ISS, if you spend 6 months there, it's about 100 millisieverts, but a trip to Mars is going to be 3 or better times that. So we need some countermeasures for that. And some of the technologies we could develop would be down in that left-hand bottom corner. They have tried out a water-filled garment, and they've tested it out on the ISS. And it would be more of personal protection equipment, but the advantage to that, water is actually a pretty good shielding material. And the advantage to this type of garment is that you could, you wouldn't have to load the ship up with water to be able to use it, because you could fill the bags and then unfill them, put it where it needs to be. And so that would save a lot of space and a lot of mass. And then on the right side of that bottom corner is a boron nitride nanotube. Nanotube technology is being looked into now as possible shielding materials. Aluminum's great, but to go from the Earth to Mars, we're going to need something a lot more resistant that provides a lot more shielding. And nanotube technology, especially if they're hydrogen infused, that's a possible really good option, but we're still pretty much in the early stages of that one. The other huge health risk is the long-term exposure to microgravity. Again, thanks to the ISS, we have a lot of data on what 6 months to a year does to the human body in microgravity. We evolved to live in our nice little gravitational field. So when that changes, that causes some ill effects on our health. And the countermeasures on the ISS include things like conditioning and resistance training. Something that's very intriguing would be artificial gravity. And artificial gravity is probably going to be expensive. But there has been some success with the short arm human centrifuge. And essentially the spinning of the centrifuge basically simulates gravity. And when they tested this particular one out, they did it with about 0.5 to about 2 Gs, and they saw some really positive effects of that. So we know what happens on the ISS after 6 months in microgravity. That's how long, you know, on a good trip it would take us just to get to Mars. And so in order to travel to Mars, we are going to need to develop better countermeasures. Or people would, the muscle and bone degeneration would just be too much. And then over on the right-hand side, just some technologies that use the planet's resources for when we get there. Because like any other trip, we can't pack everything we need and take it with us. 3D printing using the Martian regolith as material for the 3D printer would be very useful for providing habitats rather than having to cart supplies to build them. Another one that I find very intriguing is the MOXIE that's been tested out on the rovers on Mars and producing our own oxygen from the CO2 in the Martian atmosphere, because we're going to need oxygen to get back off the planet and for various other things, and to transport that amount would be very expensive and very cumbersome. And then intercropping on Mars, that we've been able to, and intercropping is putting different types of plants close proximity, kind of like gardening. And we've been able to show some progress on that in growing, especially tomatoes in the Martian regolith. And if we could mix that with maybe some other types of soil to facilitate that, that would be extremely helpful if we're going to ever establish any kind of habitat or colony on the planet's surface. And I know I am really pushing the time limit.
I was just about to say maybe 1 minute more.
Oh, yeah. Well, brevity has never been my strong suit.
Well, it was a fascinating presentation and such an important topic. I think so well in line with the topic of this whole conference, in how do we further space and prepare for space exploration. You touched on some really important points. So thank you so much, Sherry. Really appreciate it. Great presentation. I've seen some questions come in in the chat. So I'm gonna kind of scroll up and make sure I can I hope I am not missing any. If I miss one, just please put your question in again, and I apologize. But the first one I see here is a question. I believe this is for Luis. Luis, the question is, have you considered a touchless interface paired with the screen? This is in using the Manet tools with the spacesuits.
Hey, yes, can everybody see me? I'm sorry. I'm trying
We can hear
to
you. Yeah.
I'm trying to share my screen, but it's not doing it. I was
You
gonna
need to
show I
share
was
the
going to show another picture, but it's just a different picture of the display that's in my presentation. It actually turns out that you can deactivate button usage on the device and just use joysticks to move around a cursor. So you actually can enable the device to have a touchless interface. The problem is that you still need to touch buttons to confirm options, right? So you can use the joysticks and put the cursor over what you want, but you still need to press a button. This is answering Sudeep. So we tried it. I tried it a lot, and I tried it during day and night missions. And I do think that the best way to do it is just as a reference only rugged display controller. I think if we could have another way to confirm options with the joysticks, it could be possible. But with the current device, it was not possible because the buttons are they're very hard to press with the pressurized gloves.
Excellent. Thank you so much. Jason, there's a question for you in the chat. The comment is very exciting work. How does Charon compare? Is it very similar or notably different to what you presented about Pluto?
Yeah, there definitely are similarities. One of the things that I found was that some of the sublimated material that eventually makes its way to the upper atmosphere and escapes the upper atmosphere actually lands on Charon, and could be possible, could be the reason why we have why there's that reddish material on it, the tholins that might be on there. So it does that, and there's also it's locked with Pluto, so it actually experiences similar seasons. So it does have some sublimation on it as well.
Oh, thank you. That's really interesting. So we have a couple of questions from Jason for some of the presenters. Michael, a question for you. Are there any outer solar system moons that you plan to compare impact cratering of Vesta and Ceres with?
So that's a great question. Yes. So I've done comparisons with Ceres to other solar system bodies like Mercury, Mars, and the Moon, as well as Rhea, Dione, and Tethys, and also looking at Ganymede. So continuing the study to just kind of add to that full list is the plan. So looking at the icy moons of both Jupiter and Saturn to help compare, especially understanding, the asteroid belt in and of itself. Has there been migration and things of that nature?
Really interesting. I know there are a lot of theories right now positing the degree to which migration has occurred and the factors that have influenced it. So this is a really interesting way to look at it using the JMARS software. Ian, we have a question for you in the chat. It says, can you tell us some more information about the telescope in Utah? And I'll add on and how it could help with the project.
So the telescopes in Utah have been one of the interesting ones we've got some observations on. Our observations haven't been complete. We did have an issue with one we got where it appears that it started about an hour late, so we got a partial light curve out of it, which I was absolutely ecstatic about. I was able to compare that light curve to other people's, and it was very similar. I unfortunately don't have very many details on it. Those I keep on notes, and I don't have the notes on hand. But it is, I would consider one of the probably the second most site that we've tried, and we get access with that with help from Terry, and we usually put in a request. We have a bunch of observations. We put in the request for the ones we want to do, and then a way to get data back. But as far as specifics, I'm sorry, I don't have any easily accessible on hand.
Nice, thank you so much. That's great information, Ian. Sherry, a question for you. Could there be long-term vestibular issues going between microgravity and artificial gravity, considering the extended times that we're talking about?
Yeah, on that one, and that's not my area of expertise, but yeah, I would definitely think that after that long of a trip, to go from the microgravity, just the planet's surface, I think we're going to have to figure out how to mitigate that, because even that's going to be a bit of a change. And I don't know if like slowly incrementing it, like I don't know what the solution would be, but I really do think we'll have to figure out some sort of artificial, like we're going to have to figure out a way to counter that.
Very good point. It's the more you think about, when you first think about going to Mars or any other off-world destination, you think about the big things that need to be addressed. And certainly, you gave us some really great insights into them. And then you get into the nitty-gritty, and it's not just the different gravity, it's all the different gravities along the path. So really, really excellent point. Thank you. Sherry, one more for you from Luis. Did you encounter any research on the different resistance training requirements between the ISS in microgravity and Mars with 1/3 of Earth's gravity?
Not specifically on that. What I came across a lot of was what they do on the ISS and the way the exercise equipment has evolved over the last several years, mostly. Again, that's something we're going to have to address if we go to Mars and go to the surface of Mars, is how we're going to deal with that part. The 1/3 Earth's gravity, like how will that affect the equipment we use there, how we do things, or unless it's a one-way trip, we can't really run the risk of totally adapting to that, I don't think.
Thank you. Good insights. I appreciate that. Michael, I believe this next question is for you. It says, can you train machine learning models to analyze different asteroid impact craters to save time on research and also find correlations to predict asteroid movements for Earth space travel safely?
Okay.
Travel safety. Sorry.
You're good. This is a very interesting question. So we talk about this a lot at the Planetary Crater Consortium, which happens once a year. And we talk about integrating machine learning into impact crater studies. It's a loaded question. The answer is yes and no. You can use machine learning to help automate some of the systems to look at impact craters, but they have a lot of limitations. And a lot of it has to do with the degree at which it's pulling the data, also identifying if something's a circle or not is a whole another issue. A lot of the machine learning, from what we've seen, return values that, for example, we'll say a mountain's a crater because it looks like a circle and it's not really a depression. It can't really identify crater depth because of shadows and things of that nature. So while you can use it to find circular objects across the surface, it's best to then go back and investigate manually to ensure that it actually is, in fact, what you're looking at, which is why it sometimes is just easier to go ahead and just do it by hand to kind of cut out the middleman in that sense. But it does help with other pieces like statistical analysis and looking at different values of frequency across the board if you're doing like particular parts of the study. But when it comes to the counting aspect, there's still a lot that needs to be worked out. And we've been working to try to figure that out. As far as correlations to predict asteroid movements, I know that there have been several dynamical models that have talked about collisions, which we use for crater statistics to identify impacting rates. So that has been done and they're continuously being improved. So I guess the short answer is yes.
Thank you. Yeah, I imagine that quite a bit of validation would be needed to really trust a machine learning model when you turn something over to it. And that, we might be there one day, but it sounds like we're not there yet. So unfortunately.
They identify between 20 and 40%
Ooh,
is essentially where we're at right now.
not
so.
really the percentage you want to base a
Right.
conclusion on for sure. So thank you. Jason, I have a question for you. Pluto's atmosphere has been compared with the coma of a comet. Based on the research you did, how accurate would you say that description is?
I would say that that's pretty close because there's comparisons of the makeup of the molecules and atoms that are on Pluto compared to a comet. Another one that actually is even closer would be the plumes from Enceladus. That was another thing that I was looking at in my last class, and those the different charts on there, they were very close to each other. So there's definitely similarities between that. Yes.
Interesting. Yeah, it's an interesting point because it has it weighs in on the whole debate, which has been settled but still continues to exist on whether Pluto should be a planet or not. And when the atmosphere was first discovered and there was a big uproar, sort of uproar over it, I think understanding that it is an atmosphere and yet it's not necessarily the same as a planetary atmosphere. In some ways, yes, in some ways, no, right?
Yeah,
it's not something that's unique to planets anyway.
Yes, it's interesting, and I remember a couple of years ago there was the every year they do the space symposium here in Colorado, and speaking with one of the speakers, they mentioned that what would happen if you took Pluto and moved it closer to the sun, and they're like, it would form a tail. So they're trying to argue why it's not a planet, but yeah, it's very interesting.
Absolutely. Absolutely. An interesting object, no matter what classification it fits in, right? Um, Ian, I have a question for you. And this is not only a question based on the talk, but something I'm interested just to know, from your perspective, what lessons learned, will you apply forward in your work with the brand new Team 2 for the exoplanet research process? What things have you learned from being part of Team 1? And for everyone's information, Team 1 really was kind of a guinea pig. They forged the way. And so I'm interested to hear what you will apply forward to, as you begin with Team 2.
I think the greatest benefit we can provide for Team 2 is a faster pace. And that is to say, like, I met with them last week and I explained to them that we have plenty of time, but through mistakes we've made along the way with Team 1, just kind of where we had to try something, for example, trying to generate a light curve and it failed. I was able to make notes and say going forward, okay, this is the kind of error we're getting. I have to go back, I had to research why we might be getting that error, ask questions. Going forward, I'll be able to say to the team, hey, if you see this, this is most likely the cause. And that would speed up, I believe, time that they would have to work on trying to locate or figure out any issues. Second to that, I would say the next best thing is being a software engineer. I'm really digging into the software and I'm making notes as we go. And some of the software has steep learning curves, so I'm trying to put together a guide that might kind of speed it up, get everybody interested, but at the same time show them how to do it themselves. That way it's retained, you have muscle memory, and it just becomes everybody on the same page, everybody knows how to use the software, and it becomes more cohesive.
Excellent insights. Thank you. And thank you so much for your work with both Team 1 and Team 2. You've been an amazing leader in this project.
Thank you.
Let's see, a question has just come in. Jason, I believe this is for you. Or anyone could really point on this, but it says, can planets or large bodies with a strong enough magnetic field at the edge of the solar system be harnessed for generating electricity as a charging station for deep space probes? It's an interesting question. I'll actually open that up to anyone on the panel. But if anyone would like to jump in and with some thoughts. The idea of a deep space charging station is certainly a very interesting idea. The only planet that I know of, at least in our solar system, that has an incredibly strong magnetic field would be Jupiter. That's the one with the really, really strong magnetic field. Although, other planets have magnetic fields as well. Harnessed for generating electricity. It's interesting to think about the kind of technology that would be needed in order to do that. I certainly don't think we have that capability at the moment, but it would be, and thinking about starting close to home, it'd be interesting to develop that technology to use the Earth as a charging station, just to get us to the moon and Mars, right? I don't know. Any thoughts from anyone? Space tethers, interesting.
It
Go ahead,
sounds
Jason.
really awesome. I would be concerned about the radiation damage to the charging station. Like, we would have to figure out a way to reduce the radiation over time, or we'd have to keep manufacturing them, sending them out, and then once it's dead, figure out a way to dispose it. But it's a really cool idea. That sounds awesome.
Yeah, it'd be amazing to be able to harness that energy. Shielding would probably be a problem, but that's a really good idea. But yeah, if we could do that here on this planet, that could be helpful as well.
I'm picturing little EV charging stations throughout the solar system. So
Little
Tesla might get into the whole rocket market at that point, perhaps, you know, Elon's already there, so he can just kind of merge it with what he does with Tesla. I don't, it's a fantastic idea, and I appreciate the question. Very, very interesting question. Well posed. Thank you. Luis, I had a question for you. If you could, I know we've talked about this a little bit. If you know, if you could get the equipment for a second round of testing, what would be your you know, top on your wish list to test with the MPU-5s?
Oh, I think I think I would want to lean a lot more to figuring out before the mission how to correctly mount the radio to the back somehow. There has to be some harness that can get the radio out of the way, because realistically, that's how it would be done in a mission, right? Completely out of the user's way, and to integrate the detached push to talk buttons with the suit. After that, what I really would like to use is, I think it would be cool to do search and rescue scenarios with this device, because the scenarios that you can set up pretty much are where one person can always see the other person's updated position, right? So I'm gonna use the Mark Watney example again. You know, you would not have that situation where they're like, where is he? What's going on? You know, the ridiculous Martian storm. You would have a actual posit rate position on this person. So I know it was one of the test cards and we just could not get to it with inclement weather, but I would like to delve a little bit more into the applications using the suit without the rover, and still going into those situational mission-centric tests of the system. Because I think one thing is to mount the unit, but another is, hey, we can start looking into what kind of capabilities do mesh networks give an astronaut on another planet, and one of those is search and rescue capabilities. It's just, that's one idea that was in the back of my mind when we're out there.
Nice, excellent idea. I love that. Oh, and Luis, one more question for you from Jason. Could integration with search and rescue personnel, such as the ones we have here in Colorado for mountain rescues, help you with that effort? So could we apply the same techniques and procedures?
I don't know, because the situation, the testing would be centric to ILMA, to the University of North Dakota, because that's where we have the spacesuits. So it would have to happen there, and I think the insurance on the suit is like $10 million. So I don't think they're gonna let us put them out there in a cool, like, realistic location, you know, like Utah, or Arizona, something that looks like Mars. But I think for the establishment of tactics, techniques, or procedures for SAR personnel, that would be an awesome integration, especially because a lot of these guys know how to use MPU-5 specifically for search and rescue. So the lessons learned from those guys would be huge. So I think I would, if I had the opportunity to talk to them, I would integrate them into the lessons learned that they've brought to the field for that.
That would certainly be really interesting, and at least some sort of collaboration, like you say, to pass on those lessons learned. It looks like we have time for this one final question. This is from Sudeep. Could spacesuits be plugged into communication towers for a better connection if your equipment is glitching or not working? It's interesting.
So this goes into, you're putting me on the spotlight. This goes into mesh network theory. And the idea is that you don't need a central node. In communication networks nowadays, a node, right, or an access point would be a communication tower. So MPU-5 radios, when they say that they're self-healing, in layman's terms, it means that one of these radios can turn into the master node and coordinate everybody's different access points. Another really sweet way to look into this is that if you were to plug one of these radios with an Ethernet cable and have access to internet anywhere, that one radio could disseminate data to everywhere else and receive data for everywhere else and plug it back into the Ethernet. So this theory of mesh pretty much eliminates the necessity to have one single access point or a central command node, right? So in the question, if equipment is glitching, another node would pretty much prioritize receiving that information, right? And rearrange the hierarchy of those nodes while you were out there. The cool thing is that they do it automatically. They're really smart and it requires no user input. When you're out in the field, you would not even notice that it's happening. So it is a very different shift from the traditional push to talk radios that we're used to. And that's why, Jason's search and rescue friends, like that's why they use them, like it's rugged terrain, like you're not going to have access to fancy internet out there, but one of these devices can be the central node and you only need pretty much one node connected to the internet and everybody is pretty much set, good to go.
Excellent. I'm so sorry we are out of time, so we're going to have to pause there, but that was an excellent answer and excellent presentations. I want to thank all of our presenters. You've given us just some really amazing presentations and amazing topics. Thank you so much. And thank you to everyone for listening, for being part of this. We'll see you all in a future session. Thanks everyone for being here.